In this video, we're going to be covering sequences. Let's start with the aRange function. When we write np.aRange from 0 to 20 with a step of 2, it creates a sequence starting at 0 and increasing by 2 until it reaches, but does not include 20. Remember, NumPy's aRange stops just before the endpoint, so the sequence ends at 18. If the step were 1, it would stop at 19. If we set it to go up to 20, it would include numbers up to 19. We can reshape this sequence of 20 elements, but we have to make sure that the total number of elements is divisible by the number of rows or columns we want. For example, 20 is divisible by 4 and 5, so we can reshape it into 4 rows and 5 columns, meaning 4 brackets each containing 5 elements. Now let's look at NP linspace. Compared to aRange, linspace is especially useful for creating evenly spaced numbers. For instance, if we create 10 evenly spaced numbers between 0 and 20, this function includes the endpoint 20. Linspace is commonly used when building graphs or visualizations because it allows us to control the spacing between values precisely. In machine learning, linspace can be used for grid search, where we test multiple parameter combinations. By defining a range of values, the model can evaluate which parameters lead to the best generalization performance across different datasets. To clarify the difference between aRange and linspace, aRange uses a fixed step size, such as every second number, while linspace generates a fixed number of evenly spaced values between 2 points. There's also a function called logspace, which creates values spaced evenly on a logarithmic scale. For example, if we use np logspace with a start of 1, a stop of 3, 4 numbers, and a base of 10, we get values that represent powers of 10. This is especially useful when plotting data that spans several orders of magnitude. A log scale helps compress large ranges, making plots easier to read and interpret, especially for log-log or semi-log graphs. Now let's move on to random number generation. First, we have random numbers from a uniform distribution, which generates 5 random values between 0 and 1. Next, from the normal distribution, we can generate 5 random numbers drawn from a bell-shaped curve centered around 0. We can also generate 5 random integers between 1 and 100. Each time we run it, the output will change because the numbers are sampled randomly. Here's an example of random sampling and shuffling. When we sample with replacement set to false, we select unique elements, meaning no repetitions within that draw. However, if we set replacement to true, repeated values can appear since each element is returned to the pool before drawing the next. Finally, we can use permutation to shuffle the elements of an array. This rearranges the order of items randomly, which is often useful in tasks like randomizing data before training a machine learning model or performing cross-validation. It just reshuffles the array, and you can see that the order changes each time. Now, here's something very important: the np.randomSeed function. This function fixes your randomized results. It's important because when you're comparing models, you want to ensure they are evaluated on the same data set. By fixing the randomization component, you prevent small random perturbations from affecting your modeling results. This allows you to isolate the randomization and make fair comparisons between models, since they will be trained and tested on identical randomized data. As mentioned earlier, np-random-ran generates numbers from a uniform distribution, but you can also use more specific statistical functions. For example, if you simulate rolling a die 6 times, you would expect each face to occur with roughly equal frequency because each has a 1 in 6 chance. However, due to randomness, some outcomes may appear more often in a small sample. Here's an example using a normal distribution. You can set the mean, also called the location, and the scale, which represents the standard deviation. These two parameters are common across many distributions, but in the normal distribution, they correspond directly to the mean and standard deviation. Next, we have the binomial distribution. Suppose we take 5 samples of 10 flips of a fair coin. Each number represents how many times heads occurred in those 10 flips. For example, in the first trial, we might get 1 head, in the second 3, and in the third 5. These results can vary, but they follow the same underlying binomial process. Now consider the Poisson distribution. If lambda equals 3 and the sample size is 5, we are simulating arrivals that occur at an average rate of 3. This could represent something like customer arrivals per hour. For instance, in one simulation, 2 customers might arrive in the first hour, 2 in the second, and 2 in the third. In another simulation, it might be 3 in the first hour, 2 in the second, and 6 in the third. The results differ each time, but on average, the rate is about 3 arrivals per hour. Random number generation and these statistical distributions we've discussed have many practical uses. One of the most common being synthetic data generation. Synthetic data, often called fake or test data, is artificial data created to mimic real-world data. It's useful when actual data is limited or unavailable. For example, consider a cold start problem. Suppose McDonald's wants to test a new product like a Rocky Road McFlurry. They already have sales data for the cookies and cream McFlurry, but none for the new flavor. Since both are ice cream products with similar seasonal demand patterns, McDonald's could generate synthetic data for the Rocky Road flavor based on the mean and standard deviation calculated from the existing McFlurry sales data. We can simulate a weekend effect by slightly increasing sales using a random uniform multiplier between 1.1 and 1.3. When we plot this data, we get a realistic-looking graph showing seasonal patterns and weekend bumps. This simulated dataset represents synthetic data. It's random, but structured based on the real data's underlying patterns. So that's it for random number generation and sequences. In the next section, we'll be working with a common problem, missing data.